This is the initial final electrical inspection data sheet where we go through consistently a series of tests, phase-to-phase resistance, insulation resistance to ground, DC high pot where customers agree, and a surge comparison test. And then this is one of those places where we have some of the voltages referenced from various IEEE standards that are right on the form. So our guys don't have to look for it. They go to the chart and they identify, like if it's 4,000 volt and it's a new winding, you're going to high pot it at 15,000 volts, and that follows an IEEE standard for DC high pot testing or surge testing. If it's an old winding, we reduce that voltage, and those are all following IEEE testing or ESA. And then insulation resistance to ground, the same thing, following IEEE 43-2000, where they recommend voltage levels for different voltages of the machines, that kind of stuff. So the form was laid out so you had initial and final, so that when you take the initial and then you finally do the final, you're looking at that information and comparing and making sure that the final in all cases is better than the initial, or it raises a red flag. Tests are performed in the order shown, as I said, phase-to-phase resistance and insulation resistance to ground. If it doesn't pass those, we don't move forward to the other more what we would call potentially destructive tests. So test instruments, we have several of these throughout our facility. A low ohm meter measures down to the micro ohm, 10 to the -6 for the engineers that are in the group, but it measures very, very low resistance up to about, I think it'll read up to about maybe 10 ohms. So it goes 10 ohms and all the way down. Very handy device. Insulation resistance tester. This is a multi-voltage unit, 500 volt, 1,000, 2,500, and 5,000 volt, I believe. And that helps us when we're doing those IR tests or polarization index. DC high pot tester, this one happens to go up to 75,000 volts. Why would we need that kind of voltage? Well, for 13,800 volt machines, you're testing up into the 40,000 range. But sometimes you'll have customers that say, hey, take that sample coil after it's been VPI'd and test it to failure. Where does it fail at? So having the ability to try to do that. Sometimes we can't. And then this device is really cool. It's one of our newer ones. It's a multifunction surge tester, kind of like a Baker, but it's another manufacturer, Electron. They've done a really good job of automating the testing so you can connect it. You put in the information about what the motor is, particularly the voltage, and then you select a parameter for testing, and it will go through the testing automatically. It'll do the phase-to-phase resistance. If it passes, then it moves to the insulation resistance, and then the polarization index, and then the DC high pot and the surge. It will go through all those. There's a few steps that you have to take for safety. Great device. Polarization index is essentially insulation resistance to ground over a 10-minute period, and you're documenting the 1 through the 10-minute values. And then you take the 10-minute value ratioed over the 1-minute value, and it gives you a ratio or a number. And it's meaningful when you track it over time. And it can be meaningful even in when you look at a unit just one time. But all of these are more meaningful when you can track them over time. Helps you identify insulation condition and cleanliness, guided by IEEE 43. And again, all of our tests are following or being guided by standards, whether they're ESA or IEEE or married together. A lot of ESA is IEEE regurgitated. Sometimes we have to clean the winding. So I'm jumping around because I was thinking about what happens when we get to certain parts of the dismantling process, or what happens. Sometimes the windings are so nasty, dirty, you can't really do a good visual inspection. Electrically, they might test bad, but is it bad just because they're dirty, or is it bad because it really is grounded or has a shorted turn or whatever? This particular motor had water up to that line. Over-greasing, just different things that we look at. So Sometimes we recommend cleaning it before we even get to the quote process, so we really know what we're dealing with. Armatures. Very important on armatures. They come in usually with lower megger values. DC motors will operate at much lower insulation resistance or megger values than AC, and they can operate very low, but sometimes there are recommendations to rewind them, and maybe you don't have to do that if you can actually clean it properly. We'll talk about that a little bit. And then cleaning and baking and retesting and going through that process. So armatures can appear fairly clean. Carbon and dirt can be hidden underneath, behind the com, underneath, inside, and that can actually bring that insulation resistance value down. So a lot of times you can, if doing proper cleaning, and there's a lot of different ways of doing it, you can bring those numbers up without it just automatically being a rewind. So example of a dirty winding, just quickly, doesn't look too bad other than it's had an oil leak, obviously, and some contamination. After you clean it up, you see an iron rub. You see where the rotor had drugged the stator in the past. So just things like that. Specific to DC motors, this form is a insulation resistance form for shunts, series, interpoles, armatures, armature, and so on. Brush holders on incoming, after we clean it and bake it, in final. And we like to put those all together so that we can see everything collected on one form. We compare them, like I said, at the various stages. IR to ground, a quick note, it's inversely proportional to temperature, right? So if the temperature is higher, the insulation resistance will be lower. So there's a relationship, temperature and insulation resistance, that you have to pay attention to. So what that really means is IEEE defines this in 43-2000 that you need to correct your values to a common temperature. So they show you how to do that. We correct them to 40 degrees C. So now I could take that reading that might have been done a year ago at 70 degrees F, and this IR reading today that might have been done at 90 degrees F, and I correct them to a common temperature. Now I can compare an apple and an apple. If I try to compare it before you do the correction, you're not looking at anything that will make any sense, or you'll make bad decisions. So DC voltage drop testing. The best way to identify if you have turn shorts or issues in the fields, the series, shunts, series, or interpoles of a DC is doing voltage drop testing. We do AC and DC. So we will apply DC voltage to the fields just like they were energized, depending on if they're in series or parallel. And we'll actually physically do take a voltmeter and do a voltage drop measurement across the field. And that will tell you if you have shorted turns, because as the turns get shorted, the resistance gets lower, and that changes the drop. It's simple Ohm's law, V equals I times R. If you do the math, you can see how simple it is. But it works really well. And then we do AC, because AC, even though it's a DC motor, 60 Hertz has the ability to find more problems in the winding than the direct DC does. DC is a little more forgiving with insulation degradation. AC will show it up right away.